Hello everyone, my name is Members Brivin and I'll be taking you through a review of a journal, a computational attention mapping deep neural network for classification and localization of cardiomegaly on chest x-rays. So apparently this journal was given to me by, by the lecturer and we are supposed to review. So when I was reviewing, I found out that cardiomegaly is a heart disease that makes the chest to swell and it leaves some signs. And the guys who are working on this model, who are training this model, they are training it in a manner that when that model is provided with X-ray images of someone affected with cardiomegaly, it should be able to tell if he has that, if the disease is, if the heart is infected, and other thing, it should be able to tell the part of the heart that is infected with that disease. So those are just my details, and I'm relating this to our project which we are working on with my fellow colleagues. It's an explainable machine vision technique for fish detection. We are trying to train a model, an AI model that can be able to see images or pictures and tell if a fish is infected or not. So let me take you through the review. So generally, uh, these guys were working on a neural network structure. This is how when I finished the review, this is how I saw it. It was a neural structure designed for detecting, like I told you, and it involves two things. One is classification, and classification is identifying whether the the fish, the heart, rather, the heart is infected, like the presence of the disease, and then localization, which includes identifying whether the disease, where the disease is present in the image. Like it has to be able to tell the heart is infected, and this part of the heart is that which is infected. So the computation problems they feel like they mentioned on my review, one was medical image preprocessing. This involved tasks like segmentation. Segmentation generally is a process of partitioning an image. Yeah, it's a process of partitioning an image into multiple regions or segments with the goal of simplifying it, or simplifying its representation so that it's easier to analyze. Yeah, in their computational problem, they mentioned that a segmentation and then identification, the identification of the part of the part of the heart which is affected, and then uh, the second computational problem they faced was handling of big data. So apparently, these guys had input a lot of data when they were training, and it became a problem for them to handle, to interplay with training, validation, and testing. So the other problem was casual or explainable and universal visual medical diagnosis. So, like when they were providing the classification outcomes, such as the spatial regions, the segmentation of abnormalities, the location. So it, like for how they had treated in their journal, it was also part of their problem. And then also visual expansion supporting classification of outcomes. Here they okay they couldn't explain like they couldn't explain the decisions made the model they were making, meaning it was providing collect information, it was providing collect outcomes, but themselves they couldn't explain why it was giving such answers. And then there's also the last one, efficiency of reliable models. Uh, Developing a reliable model for medical images involves addressing a lot of challenges, mostly related to training, optimization, and evaluation. Here, it's because when it's a medical problem, you don't have to judge around. You don't have to make a lot of mistakes. So that's why it's a problem also. So uh, so the models they used one was the neurophysics classifier. In the journal, they say it was proposed by Torres, and it was in for detecting of of the disease in the dictator cerebral. That was the classifier. So the other one was convolutional neural networks, and this was they used three of them. One was the transfer line up learning approach, uh, which was to classify by observing several convol- con- convolutional networks, yeah, architectures. Then they used the UNet model, and it was combined by the DESNet. That's what they had classified their models. This one was for segmenting and baseline classification. Yeah, segmenting and baseline classification for like for detecting the disease. Then the other one was the 121 layer convenient model. It was detect. It was that one was for detecting various diseases. That's how they mentioned it. Then the other model they used was the dilated convolutional layer, which was uh, that one was for segmentation of microtonal and blood pools in the cardiovascular. Those are very biological terms, but that's how they mentioned it, that it was for segmentation of the blood pool and myocardium. Then they also used the routing by agreement method. That one was for classifying of the thoracic diseases, which includes the one I had mentioned before, the cardiomegaly. Yeah, and it was used for model interpretability, I think. So the next one was attention mapping mechanism, which was to improve this. It was not to improve the precisions and localization capabilities. Yeah, that's also that's it was part of the models they used. And then also the last one they used the CardioX attention net, which was for integrating uh, various advanced convention networks architecture. This one was for integrating them. Then when we go to the yeah, like I was saying, from the image you see, they were able to input a chest X-ray image, and then in the model, then the model was able to process and tell that this part of the you can see the part in kind of green and rainbowish colors, that it shows that this indicated part of the heart is infected. So that the algorithm was the model was 96.7% correct according to the builders. So moving on. Yeah, so here we go for the model analysis and techniques applied, and these are the models, the model analysis and the techniques they applied for their model. So the first one was soft attention mapping mechanism, and this technique enhances the goal average pooling method by providing a weight parameter. Yeah, so for them they provided a parameter with a range of 1 to 0, and it allows the model to focus on parts the input on focus on relevant parts of the image, This improves the localization capabilities as I had defined for you what localization means. So then they also use transfer learning, uh, like it's used for training the model from scratch. Yeah, these guys they mentioned that they are training their model from scratch, and it's very possible to use for pre-trained weights from image demonstration potentials. Uh, it's a very good model. It's a very good analysis. Like I checked about it, and yeah, though it's complicated. So there's also stochastic gradient descent. So this one is for optimizing the algorithm used to train the model. Along for these guys, they use the momentum of 0.9, update the model parameters. Uh, they did it several times iteratively. They are basing on mini batches of data. Then there is also mini batch training, and they use a mini batch of size 16, uh, which this one helps in training efficiency and reducing memory requirements. That's how they had set it, but I don't know how it was able to reduce memory requirements, but that's how they had set it. There was also learning rate annealing, and they had initialized it at 0.001, I think, and they annealed it at the factor of 0.3 after 15 epochs. Whenever the validation loss stopped improving, uh, then there's also model checkpointing. Here they were checking the model with the lowest validation loss and saved it during training, and it served up as a backup point. Like when they would go further and then the model starts misbehaving, they would come back to that point, the lowest validation model. And that's how they mentioned it. And then there was also early stopping. Like I told you, a model which had the lowest validation loss, like it was saved during training, and no, that's model checking. I was on early stopping. Early stopping. That one I don't really recall, but I think I can check. Let me first check. Yeah, so I've checked, and they here they used to stop earlier enough if the validation loss doesn't improve. So they had specified for 40 epochs. Whenever it didn't improve on 40 epochs, they would stop using that. And this one, it helped them prevent overfitting, and it also improved generalization. So this takes us to the strength of their model, and for them it was we had customization for specific domains. For them it was easier because they would like I have been telling you, they were able to specify, like to work on a single domain, then they just add it within the model. Then the flexibility in training parameters, all these have been explaining them. Then regionalization and generalization, efficient resource utilization, all that is what I've been explaining.